Chateliers principle in more detail. We did the lab yesterday, but basically there are things that are going to perturb the equilibrium. And so from Le Chatelier's, there's going to be a system at equilibrium. System at equilibrium is the reaction has already run its course and wherever it ends up. You know, for example, if it's steep downhill, then it's all products. You know, if it's steep uphill, then it's all reactants. But if it's not so steep one way or the other, you're going to have a mix of products and reactants, and that's where it's going to end up. That's where it's going to stay. There's going to be no further reaction. And so what we're looking at is at the end of the reaction, at equilibrium, we could perturb things, we could upset things. And so we could add some, let's say we added some chloride, you know, to precipitate out silverines. Well, it would stop there. Once we stop adding the chloride, we'd reach equilibrium, but, you know, we can continue adding chloride, more chloride, more chloride, and then it'll push the equilibrium one way or the other. And so we have a system at equilibrium, we perturb it, and then there's a shift. Now, the ways we can perturb it, is this. We can increase the concentration or decrease the concentration. And so increase, decrease concentrations of reactants and products. Perturb means to upset it. Like say, if I had things perfectly balanced here, I can perturb it by just adding another pen here, and then it screws up the balance. Okay, it screws up the balance, and then we'll reattain a new equilibrium system based on that. And so how do we upset the balance? Well, by changing the concentrations, that'll upset the balance. And so increase and decrease the concentration of the products or the reactants. You can increase or decrease the pressures of the reactants. We can increase or decrease the volume. Now, volume will have an impact on pressure and concentration. The smaller the volume, the higher the pressure, the higher the concentration. The bigger the volume, the lower the pressure, the lower the concentration. So volume can do that. These will perturb. And what we had is we had a system at balance, but the other thing here is we can increase or decrease the temperature. Now, temperature is unique because temperature changes the balance. You know? So what was once well balanced at one temperature, if we change the temperature, it's going to shift the balance one way or the other for certain reactions.
Like what's the symbol above
Pressure?
pressure?
P.
What was it again?
P? This one? Oh, what's that symbol? This is the molar concentration. Molar, and the square brackets mean molar concentration. The way this does it is increasing or decreasing temperature doesn't change necessarily certain characteristics here. This changes the balance, changes K. Whereas when we change the concentration, we change the pressure, we change the volume, that doesn't change K. You know, the K is whatever balance we're supposed to have. But when we mess with the temperature, that changes K. And so the original conditions, which we could still maintain, which were balanced, are no longer going to be balanced. Now, there's some tricky things here. And so, note, adding, like, for example, increasing or decreasing the amount of pure solid or liquid has no impact. And the reason it has no impact is, let's say if you have a half gallon of milk versus a gallon of milk, is there a difference in the concentration? And no, there's no difference. So if difference, there's no difference in concentration, there's no difference in reactivity, right? So there's a big difference. Let's say you had 100 milliliters of 6 molar HCl and 200 milliliters of 6 molar HCl. Then you think, oh, it's HCl, it's going to have certain reactivity associated with that, and it's going to be comparable. And so 100 milliliters, 200 milliliters, you got more with 200 milliliters. Versus if we had 100 milliliters of 6 molar HCl versus 100 milliliters of 12 molar HCl, then you're going to treat those quite a bit differently, wouldn't you? Because 12 molar HCl is going to be much more reactive, much higher in terms of concentration and much higher in terms of what we call activity. And so this has no impact. Okay, then we have increasing or decreasing pressure by adding or removing an inert gas. If we increase the pressure by adding, let's say, helium gas, and helium gas doesn't participate in the balance at all, then it's not going to upset anything. So let's say I'm dealing with carbon monoxide gas and other gases here, but if I add some helium doesn't go on the balance at all. And so there's no tipping of the scale. So this one's going to have no impact as well. And so let's look at some examples of this. Okay, examples we're looking at, this is from section 15.6. This is altering equilibrium conditions, Le Chatelier's principle. Oops. Turn on the projector. All right. We can sum it up here. When an equilibrium system is subjected to a change in temperature, well, if you change in temperature, that changes, again, K balance, that is product over reactant ratio. The pressure doesn't change K, if we don't change the temperature. But changing pressure will upset the balance. Concentration will upset the balance. So your system responds by attaining a new equilibrium that partially offsets the impact of the change. In other words, we have to shift things around to reestablish the balance. So here's an equilibrium. When we look at this Kc is 2.8 times 10 squared, which is 280. So crudely, it'd be like 280 parts product, 1 part reactant. But it's not quite that way because of the K expression. I talked about the K expression, right? The generic one. Is that correct? And so this is a Kc. A Kc means we're dealing with concentrations. When we're dealing with concentrations, we're only dealing with molar concentration. We aren't dealing with other units of concentration, just molarity. And so when we have a Kc, you have to make sure everything's in molarity. Did I already do this one? The Kc? No? Okay. So what is the balance? Well, here, Kc is equal to 280, 2.8 times 10 squared. And the Kc is for a given temperature, so this is at 1,000 Kelvin. Now, if I change the temperature, that's going to change Kc. It's going to change the balance there. And what this is, it's a balance between the products. And so this is a Kc, so we're dealing with molar concentrations, which I use the square brackets for. So this will be SO3 gas squared divided by SO2 gas squared divided by O2 gas to the first. You know? And so we use the coefficients as powers in this case. And this just comes from, K. K in general is, G raised to little g, G raised to little h. I did that already, right? Yeah. So that's what we're doing here. So we should always maintain this balance. This is going to be slightly favored towards the product or towards the reactant? To the product. That's what it looks like. But, the products here have a square term overall. The overall order, of the reactants is cubed, squared times first 3. So we call this third order on the bottom, second order on the top. That can screw things up when we're looking at what side's balance, what side's favored. Because if this were squared and squared on the bottom, then it's easy. This is favored towards the product. But when I change the impact of these things, then it can mix things up a little bit. But it's all right. So we think this is, and it makes sense. This is favored towards the product. In fact, that's what we see in nature. This is favored towards the product. SO3. So,
Can you determine whether it's favored towards the product or the reactants by looking at Kc?
Yeah. Basically this. We can determine it, but the concentrations can do some weird stuff. Even though this is favored to the product, since it's cubic overall in the numerator and squared overall in the whatever, it screws up when you're actually looking at the numbers, the actual concentrations. You might go, oh, that's not favored towards the product, but it is because of the order of the reaction. And so basically it's like this. If K is greater than 1, it favors the product. And it could just be by the minutest amount, because let's say it's 1.001, it's barely above 1. If K is less than 1, then it favors the reactants because you're going to get a fraction here. So it favors reactants. And so the only reason I added that little stipulation on this is because, I don't want to get mixed up, just because when we look at the concentrations, sometimes it's hard to tell, but when we look at the K, then it's easy to tell. K greater than 1 or less than 1. So here, maybe it's easy to tell which one. This is reactant, SO2, O2. These are reactants. This is product. Which one looks favored here in the equilibrium? It looks like product's favored, and that makes sense. K is bigger, so this one's not tricky in that sense. And so here we have a system at equilibrium. Products are slightly favored, so we got a little bit more. And so this is nice. And the problem is there's no more reaction. And so the reaction is, essentially the reaction has ceased producing additional SO3. The reaction actually hasn't stopped, so it's slightly downhill to SO3. The reaction hasn't actually stopped because you can't stop collisions. Once we reach this equilibrium, then there's no net change. So the amount of SO2 and O2, which is up here, and the amount of SO3 don't change, but what's happening is there's SO2 and O2 rolling downhill, but at the same time, there's SO3 going back uphill, 2 SO3s going back uphill to react. And so this is called a dynamic equilibrium. And dynamic equilibrium means that the forward reaction and the reverse reaction don't stop. It's just reached the point where for every one that rolls downhill, one rolls uphill. And so there's no net change. And so we're stuck. And so this is the equilibrium we're stuck at. There are ways to try to get more SO3. Let's say I want to get more SO3. You know, what can I do? I could try adding more SO2. If I add more SO2, then, you know, you're feeding the uphill side here, and it's going to force more downhill. Let's say I don't want more SO3. Let's say I want less SO3. How can I get less SO3? Well, I'll just increase the population of SO3 here, that is, make the concentration higher here, so that I get more collisions going up. So if I double the amount of SO3 down here, I'm going to double the amount of collisions, which is going to double the amount of molecules that can make it uphill in this reaction, and it's going to screw up the balance. So then I'll have net reverse reaction, and then, well, eventually I'll retain a balance. So that's what they're doing here. So they're actually, is that, no, what are they doing here? They're adding more SO3. And so we add more SO3, which is going to push things back uphill. Right? And eventually, we're going to get more SO2 and more O2 from that when we reestablish it. Now, the SO3 is tricky because if we add more reactant, we're going to get a shift. You know, we add more reactant, we're going to get a shift to form more product. If we add more product, we're going to get a shift to form more reactant. So we're adding more product, we're going to shift to form more reactant. And when we look at the amount of product here, we start off with 0.68 and then we go to 1.46. So if we look at it based on the initial, it looks like all of them went up. Do you see that? Both the reactants and the products went up. But when we look at the product initial after mixing, so in reality we started with 1.68. If we start off with 1.68, then we go from 1.68 to 1.46. And so the SO3 went down, the SO2 and the O2 went up. Okay, but there's common trick question. Common trick question is, you know, if I add SO3, do all species go up in concentration? And so normally when we think about this, we think if I add SO3, it's going to shift it to the left. So I get more of this, less of that. But in reality, all of them went up. All of them went up because all of them went up from the original. But if we look at the mixture prior to the shift, then the SO3 went down. And so you have to be careful. When somebody asks you, did the concentrations go up? Did the amounts go up or down? You have to say, well, compared to what? Compared to the original or compared to the perturbed initial? Does that make sense? Well, we'll see a question like that shortly. All right, so let's take a look at what happens in this example here. The effect of adding more N2 gas to constant volume equilibrium mixture of N2. So if we add more N2 at constant volume, the pressure and the concentration of N2 goes up. Which way will it shift? Right. To the right. That's it. So this is a very long answer. It just shifts right. And this long answer continues here. So we're going to skip that long answer. How about this one? Given the reaction 2CO plus O2 yields 2CO2, this is just combustion here, carbon monoxide. What is the effect of adding O2? So we increase the O2 pressure concentration, which way is it going to shift? To the right, yeah. If you're burning carbon monoxide, you want more O2, you know, more O2, fan the flame, and that's going to shift it to the right. What if I add N2? No shit, you know. So I could add air to this. You know, I don't have to add pure O2. I could just add air. Air consists of like 78% nitrogen. Nitrogen is not going to do anything to this. The oxygen will, though. Well, there's a balance here. So the balance is, let's say, like this, and then you got to have this. This is the balance. If you add more O2 here, it screws up the balance. Now we're too heavy on this side. And so what has to happen is some has to roll down so we get the new balance. It's not going to be at the same point. Both sides are going to be heavier. You know, that is because we're adding more atoms in there. Both sides are going to be heavier, but it's going to have the same balance. And so, it tilts the other way, like here. If I remove some O2, this end becomes too light. And so we have to back it up to, if this were balanced, so that we get this side heavier with atoms. Yeah. The question is if I add more product. If I add more product, it would shift to the reactant side. It just, well, let's take a look at this next one. Calcination of limestone decomposition by heating. Calcium carbonate yields calcium oxide plus carbon dioxide. Did I talk about this reaction? Yeah. So did I already go through these? No? Okay. This reaction is extremely important. This is, what was this reaction? Yeah. The Roman concrete. Okay. Well, this calcium oxide is also called quicklime, and quicklime is very important, obviously for concrete, but for other things, it's commercial. It's just calcium oxide. All right, let's see. So I have this in equilibrium. It's not a very favorable reaction, but what happens I want to make it more favorable or less favorable. Let's say I add calcium oxide. If I add some more calcium oxide, will it shift to the left? And this is very tricky because it doesn't shift to the left. It's a solid. And so the next phase of this is you have to think in terms of reactivity. You know, does that change the reactivity having more calcium? No, it doesn't. It's like milk, you know, or 6 molar HCl. You know, 6 molar HCl, if you have, let's say, 100 and 101 milliliters, is 101 milliliters 1% more reactive? No, it's just extra. You have a little extra, but it's the same reactivity. And so it doesn't change the concentration. It's still 100% calcium oxide. And so that's not going to shift it. What if we add CO2 gas? It'll shift it to the left, right? If we add calcium carbonate solid, no shift. Here I'm going to increase the pressure by decreasing the volume. Now, when I look at the volume, you know, I think that if I increase the pressure, you know, this is increasing the pressure of all the gases. So the SO2 gas, let's say I cut the volume in half. If I cut the volume in half, then the SO2 gas would double in pressure. But if I cut the volume in half of the SO2, you know, this is all in the same container. So all these are being cut in half. So all these are doubling in pressure. So the impact is the same. But the situation is this. There's a difference in the impact between the reactant side and the product side. And the difference in the impact depends on how many moles of gas we have. Over here on the left, we have 3 moles of gas. Over here on the right, we have 2 moles of gas. And so which one's going to be impacted more? You know, the one on the left is going to be impacted more by increasing the pressure. But, you know, that's starting to get too complicated. And so the easiest way of determining what happens if I change the volume is Smaller volumes favor the side with less gas. Now, a mole of gas at room temperature and 1 atmosphere has a volume of about 24.5 liters. And so that's about 25 liters. And so if I have 2 moles of gas, that's about 50 liters, plus 1 mole of gas, another 25. So this is 75 liters that the reactants occupy. If I have 2 moles of SO, that's 50 liters. And so if I compress the volume, which side is more favored? The 50-liter side or the 75-liter side? The 50-liter side, the smaller side is favored. And so this is what's going to happen. It's going to shift. If I put the squeeze on the gas, it's going to shift. And so that means some of this will react to form some of this, which takes up less space. And we're going to get a shift right. And so here I'm going from 10 liters to 1 liter. And so the pressure is increasing tenfold, basically. And what's going to happen, or the volume is decreasing tenfold. And so it's going to favor the side with fewer moles of gas. The side with fewer moles of gas is SO3 or SO2 and O2? SO3. And so we're going to see a shift. And so in other words, we start off with 0.32 moles of SO2 and we drop down to 0.17. So we lose about half of that. And then the O2, we lose about half of that. And then the SO3, 0.68 to 0.83 increase. So there's a shift to the right, a shift to the side with fewer moles of gas. And so volume, we just look at moles of gas. Liquids and solids, their gases aren't so significant. You know, a mole of gas is 24.5 liters. What is a mole of water? It's volume. So a mole of gas is about 25 liters. A mole of water is about, well, a mole of water is 18 grams of water. 18 grams of water occupies what volume? A liter. A liter is going to be, well, how many milliliters? Water has a density of about 1 gram per cubic centimeter, or 1 gram per cubic centimeter is the same as a milliliter. And so the density of water is about 1 gram per milliliter. So when you talk to chemists, if chemists say, I have 1,000 grams of water, you think, oh, 1,000 grams, 1,000 milliliters. Chemist says, I have 100 grams of water, 100 grams, 100 milliliters. You know, it's about the same. The density is about the same. So if I have 18 grams of water, how many milliliters is that? 18 milliliters. So a mole of water is 18 milliliters. 18 milliliters is not that much. A mole of steam, assuming it's ideal, a gas is 25 liters or 25,000 milliliters. So it's a huge difference. And so, you know, solids and liquids we don't really care too much about because their volume is so small. All right, so I was talking about significant reactions in Western civilization. Do you know this is another one of the top 10 reactions? Do you know why? This one increased world food output by like 10 orders of magnitude or something like that. You know, and the reason is because nitrogen is important for fertilizers. We want to put nitrogen in the soil. And so you could think about injecting, I mean, air is 78% nitrogen. So why don't you just inject air into the ground to fertilize the soil? But it doesn't work so well because nitrogen is a pseudo-inert gas. They consider nitrogen a pseudo-inert gas. Why? What do you think? What do you think makes nitrogen so unreactive? So unreactive that they call it a pseudo-inert gas.
It's a really small atom and triple bond.
Yeah, the triple bond. Do you guys know about how many kilojoules per mole a triple bond is? bonds range from under 100 kilojoules per mole, like hydrogen peroxide. The oxygen-oxygen peroxide bond is under 100 kilojoules per mole. In fact, if you have a bond that's under 100 kilojoules per mole, you have to protect it from visible light. Because if you shine just visible light on hydrogen peroxide, it breaks the bond. Iodine's the same way. I2 has a pretty weak bond. You have big iodine atoms, and it's pretty weakly bonded. So you have to protect it from light. So hydrogen peroxide, you wouldn't store in a see-through container like this, because visible light can get through this and break the bonds. Right? You'd have to store it in a brown bottle or a black bottle, something that protects it from light. Same thing with iodine. And so the bonds range from that to about 1,000. So nitrogen's about 1,000 kilojoules per mole. And it's very unreactive. There are certain things that can fix nitrogen, that is, react with nitrogen to form compounds. And those are legumes, those beans. They can take nitrogen from air and fix that. But most plants can't. So you can't just fan the plants and expect them to take up nitrogen. And so this was a very important reaction. However, this reaction, even though we think this is a good redox reaction because nitrogen should be an oxidizer. It wants 3 electrons, right, each one. Hydrogen's a good reducer, so you think there should be a good reaction here, but that nitrogen-nitrogen triple bond prevents this from reacting very well. And so the yield is extremely small for this reaction. And so, what can we do to increase the yield of ammonia? Because ammonia turns out to be a good fertilizer. Even though it's a gas, they can spray it and it's taken up on the soil. How can we improve the yield of this reaction? Should we do it in a bigger volume or smaller volume, would you say?
Smaller.
Yeah, it looks like a smaller volume. Right. Should we do it at higher pressure or lower pressure? Smaller volume means higher pressure, right? Higher pressure would be better for this. Higher pressure, smaller volume is going to favor ammonia. And so the people, who made this successful commercially, Bornhaber, they did this at high pressure. Now, temperature can also have an impact on this. And so what impact does temperature have? The way I remember the impact of temperature is think about freezing and melting ice. If I want to melt ice, higher temperature or lower temperature? Higher temperature to melt ice. And if I melt ice, is it endothermic or exothermic? So melting ice, do you add heat or do you remove heat to melt ice? Add heat. And so endothermic reactions favor higher temperature. Now, freezing ice, do you remove heat or do you add heat to freeze water? It's not freezing ice. Freezing water to form ice. You remove heat. Removing heat, is that exothermic or endothermic? Exothermic. So exothermic reactions are favored at low temperatures. Endothermic reactions are favored at higher temperatures. And so we got to think about this particular reaction here. This particular reaction, do you expect it to be exothermic or endothermic? You kind of expect it to be maybe endothermic because it just doesn't want to react, Things that want to react are usually exothermic because they're going downhill. But this is tricky because, it's that nitrogen-nitrogen triple bond that slows it down. It could still be favorable. And in fact, this type of reaction has a name. It's called a formation reaction, formation of a compound from elements. Although technically for formation reactions, we only form 1 mole of product. And this one we're forming 2, so it's a double formation reaction. Do you remember seeing formation reactions before forming compounds from the elements?
Can you re-explain exothermic and endothermic again? You said exo is taking away heat? And
Taking away heat.
Okay.
So freezing water, you got to take away heat.
Got it.
Do you guys remember Appendix D? Appendix D, we had these things called delta H sub F. Delta H sub F stands for heat of formation. And it's the formation of the compound, sometimes the element, but the elements don't really need to be there because they're all zero. And so it's the formation of 1 mole of substance from the elements in their most stable state. So when we look at formation reactions, most of these are exothermic or endothermic? Exo. And so what that says is that, you know, when we look at the world consists mostly of elements or of compounds. When you look around you, are most of the things elements or most of the things compounds? Compounds. Why? Because it's more favorable thermodynamically, right? Obviously, there's some elements, nitrogen, oxygen, you know, and air that's stable, helium, gold. You know, gold doesn't like to form compounds. Platinum doesn't like to form compounds. But most things do. And so when we look at the data, one of the patterns we see is mostly exothermic. Do you see that? Mostly. There are some endothermic. Let's take a look at an endothermic one. So let me find an endothermic one. And then take a look at that. Here's an endothermic one. Look at atomic chlorine. You know, does atomic chlorine have an octet? No, it has 7 valence electrons, 1 short of an octet. And so atomic chlorine, yeah, that should be endothermic. That shouldn't be favorable, right? CS2 liquid. Now this is an odd one. We'd have to look at that more. But some of these other ones, gaseous diamond or graphite. Gaseous diamond or graphite or gaseous carbon, that should be endothermic, right? That's not going to be favorable. And so when you look at the endothermic ones, it kind of makes sense. You know, but everything else is exothermic. These are the things we do. When we have big data tables, you know, there are different approaches that people take with big data tables. So if you look at this table's not too bad, but if you look at the table on the left there, you know, most people will just ignore it. It's just too much, you know, too confusing, too much stuff going on. But, and then we have this appendix D, which is, you know, too much, too confusing. But what you should do is you should see if there's some patterns, simple patterns, and then simple trends that you can see, because then you'll be, you know, quite a step ahead. Like, for example, here, does it make sense that delta H of formation of atomic fluorine is endothermic? Yeah, this is not going to be stable. Does it make sense that delta H of formation of fluoride ion is exothermic? Yeah, that makes sense. Highly, this should be quite exothermic. So when we look at this, I'm tempted to say, you know, when we take the, and it has a name, it's called the Born-Haber reaction. That is, if you take nitrogen and hydrogen, react them together to form ammonia. Born-Haber reaction. I had a Wikipedia page pulled up for that. And it should be favorable, and it is actually. It's just so slow to react in that equilibrium. Well, it seems favorable in terms of enthalpy here. And so when we look at NH3 gas, which we're forming in that particular reaction, it's exothermic. And so here, on the one hand, yeah, you predict it endothermic because it's such a sluggish reaction. On the other hand, most compounds that you form are exothermic. Let's take a look at these, though. There's a series of nitrogen compounds that are endothermic. Let's just focus on the oxygen ones, like nitric oxide or nitrogen monoxide, nitrous oxide or dinitrogen monoxide or laughing gas. These are endothermic. And it's a good thing these are endothermic because what does air consist of? Air consists of nitrogen and oxygen. And so if nitrogen and oxygen were forming products, that is compounds, favorably, that is exothermic, then we got to watch out because the nitrogen and oxygen air could react to form toxic gases. And these are both potentially toxic, although nitrous oxides use laughing gas. I don't know how many people died from laughing gas, but potentially toxic. Nitric oxide is important for blood flow regulation. And so you look at these oxides of nitrogen, well, it kind of makes sense in other ways, that oxides of nitrogen aren't so favorable because if we look at it, what's happening is we're oxidizing nitrogen. Well, both of these are highly electronegative. Fluorine is the most electronegative, 4.0. Oxygen is 3.5, nitrogen is a 3.0. So if nitrogen and oxygen got in a tug of war, it's a 3.5 versus a 3.0. Is that a very big difference? No, not a very big difference. And so there's going to be a struggle here, for oxygen to try to oxidize nitrogen. And you can see it's unfavorable for these. How can you make it more favorable? How you can make it more favorable is doing these at high pressure, because we're going from more moles of gas to fewer moles of gas when we make the compound. And in this case, high temperature. These are endothermic. Endothermic, you want high temperature. So where do you see high pressures and high temperatures? Where you see high pressures and high temperatures are in automobile engines. In the combustion chamber, air gets in the combustion chamber, and when you generate high pressures and high temperatures, the nitrogen and the oxygen in the air can react with one another. And that creates oxides of nitrogen. Oxides of nitrogen are called NOx or NOx. And if you have a car, you have to go get it smogged every 2 years. And what they check for are NOx emissions, because they're going to form. What you want to have happen is you want the catalytic converter to scrub the NOx out of your exhaust, to clean it. Diesels are much worse. Because diesels operate at a much higher pressure than gasoline engines. And so they generate much more significant quantities of NOx emissions. So, if I think about like in the environment and that kind of stuff, what I think is before pushing everybody to get an electric vehicle, maybe they should do something about diesel exhaust, the state of California, because the ships are, from what I understand, unregulated. They can emit as much NOx pollution as they want. And also diesel trucks, they don't have scrubbing. They're emitting a lot of pollution. And so I think getting rid of older vehicles and getting rid of these old diesels would improve air quality and the environment. Although electric vehicles are nice, they're quite expensive. The total, because I've got the electric vehicle, and the total for installing the charger with the inspection came out over $3,000 just to install the charger, and then the vehicle itself. But the cost of operation is great. It took a trip to Santa Barbara, and it only cost, I think, around $10, one way, versus if I drove my gas vehicle, which is a gas guzzler, unfortunately, but it would cost about $60. So that saved a lot. So although electricity prices have increased, I guess, 20% recently, but still cheaper than gasoline. All right, so let's go back to this Born-Haber reaction. So what do we want to do it? Now we know it's exothermic. So if it's exothermic, do we want to do it at a higher temperature or lower temperature? At lower temperature. All right, so let's see, the effect of adding more nitrogen, we got that. I'm just going to shift it to the right. Long explanation for that. Let's take a look at this next one here. Given the reaction of 2 carbon monoxides plus O2, so we're just, actually, did we already do this? We did this once here. I missed this one. Let's take the hypothetical reaction A gas plus B gas yields C gas. It reaches equilibrium, and then we add argon gas to this. What impact? Which way will it shift? Will it shift to the right or left? No shift. You know, argon is an inert gas. So it's going to react as the inert gases here. Nitrogen is a pseudo-inert gas. It's a pseudo-inert gas because of that triple bond. And this Born-Haber reaction was significant advancement, but you still have to watch out because nitrogen can react with, nitrogen is not the greatest oxidizer, but it can react with a powerful reducer. So, for example, if you have lithium, lithium and nitrogen can react. Nitrogen can oxidize it and can form nitrite cells. And so some metals have to be protected from nitrogen. So. Okay, so we're going to transfer this from a 1.5 liter flask to 5 liters. So we're going to increase the volumes. Is the increase in volume going to favor the reactants or the product? It's going to favor the reactants and shift this to the left. So we're going to shift left. And so after all this, that's what they say. To the left. Restore equilibrium. Okay, some more here. The reaction of dinitrogen tetroxide goes to 2 nitrogen dioxides. Is at equilibrium from 3 liter cylinder. What effect if the pressure were doubled? If we double the pressure, we're doubling the pressure of everything in there. And so probably the easier way of thinking about doubling the pressure is by decreasing the volume. Double the pressure, we could do that by cutting the volume in half. So if we could decrease the volume, double the pressure, which way does it shift? To the left. That's correct. So this goes to the left. This is another important reaction. This is for the water gas shift. This is another significant reaction because this is how a lot of hydrogen was produced. Hydrogen was produced by taking carbon monoxide and steam, reacting it to form hydrogen. This is a redox reaction here. Some of these redox reactions aren't so easy to predict. So what you do is you just mix it together and see what happens. So mix it together and then try to figure out the optimum conditions for this. And so what would the optimum conditions be in terms of volume? Bigger volumes or smaller volumes? In other words, pressure. Bigger volume, lower pressure, smaller volume, higher pressure. So do we want to do the water gas shift at high pressure or low pressure? High pressure, small volume, low pressure, big volume. High pressure would favor hydrogen production because why? Yeah, if they're the same, then this would be 50 liters, which side is, yeah. And so in this case, if the moles of gas are the same on both sides, then it doesn't favor, yeah. And so pressure is not going to impact this. It's not going to shift it one way or the other. Instead, we have to do some other method to try to influence this particular reaction. And that is, maybe high temperature, low temperature, these kinds of things. There's one disadvantage to low temperatures. If you go to lower and lower temperatures, things get slower and slower. And so Born-Haber, even though it's favored at low temperatures, if you go too low, you don't get much product. You have to wait and wait and wait for equilibrium to be established, but it's taking a long time for that equilibrium to be established. Well, anyway, let's take a look at this one here. And so we have hydrogen sulfide and methane yields carbon disulfide and hydrogen. This is a redox reaction too. Let's take a look at A. If the equilibrium mixture is allowed to expand into an evaporated larger container, so volume increases, the mole fraction of hydrogen increases. So if volume increases, does the amount of hydrogen increase? In other words, if we increase the volume, which way does it shift? To the right. If it shifts to the right, we're going to make more hydrogen, which means that A is true. Okay. B, if several moles of argon gas are forced into the reaction container, the amounts of H2S and CH4 will increase.
False.
False. Yeah, nothing's going to happen. C, if the equilibrium mixture is cooled to 100 degrees C, the mole fractions of the four gases will likely change. So if we change the temperature, that changes K, and therefore it's got to change. If K changes, then we can't have the same equilibrium. It's going to be a different equilibrium. And so this is true. Which way will it change? Well, it depends on which way is endothermic and which way is exothermic. When you look at this, it's hard to tell. One of the ways we tell is by, well, formation reactions are simple because we're taking elements and forming compounds, but this is not a formation reaction. And so we're taking compounds, and we've got to try to figure out which is a more stable combination of compounds, the left or the right. And in Chem 1A, one of the ways that you did that is you looked at bond energies. Which side has stronger bonds? That would be more stable. Or you looked at delta H, using those delta H of formation in appendix D. You take the delta H's of formation of the products minus the delta H's of formation of the reactants. And then we can figure out what delta H for the reaction is. Do you guys remember doing that? Okay, that's good. Because you'll have to do it pretty soon when we get back to chapter 13. We skipped chapter 13, but we're coming back to that. And so what that means is you're going to have to review things. And you might want to start reviewing some of it, slowly. Like, for example, what's the difference between enthalpy and internal energy? Or what's the difference between delta H and delta U?
You realize the temperature.
Not exactly. Both of them, both delta U and delta H will have temperatures involved because we do a reaction at a specific temperature. And so, in the ways they're very similar, in other ways they're different. And so, in what ways are they similar, and what ways are they different? Internal energy and enthalpy. And then we do things under standard thermodynamic conditions. What is standard thermodynamic conditions? What's the definition of that? And then the reason why you want to go back and do this is because you need to keep track of all the little restrictions that are in place. Because what you can end up doing is you can end up using the wrong equation for the wrong problem. Use the wrong equation to solve a problem, you're going to get the wrong answer. And a lot of people don't keep track of these things. They just use whatever equation's available. And since that's the case, then UCLA has these bumper stickers at the bookstore. Somebody did this. They went to the UCLA bookstore and bought this. honk if you pass Chem. Honk if you pass Chem. Chem deals with the thermodynamics, delta H, delta U, all this stuff. And a lot of people don't know, concisely what the difference is between delta U and delta H is. And if you don't know the difference, then if you're calculating energy, which one do you use? Do you use delta U or do you use delta H? Do you know? And if you don't know, then you're going to end up using the wrong equation at the wrong time eventually, and to get the wrong answer. And so that's why the pass rate for this class is abysmal. More than half of the class usually fails in Chem, and they have to retake it. And so, but if because me, when I was taking Chem, delta H, I don't know the difference between the delta H and delta U. I never thought about it, and then all of a sudden you're getting delta A, delta this, delta that, delta G, delta S. You got all these things, and you got to keep track of all those things and figure it out. And so you probably want to go back and look at the difference, at least between delta U and delta H, when you get a chance. Okay, so here, I don't know. I mean, we can figure out what delta H this is pretty easily, just from appendix D. D, if the equilibrium mixture is forced into a slightly smaller container, the partial pressures of the four gases will all increase. So if we compress this into a smaller container, the pressures of all four gases will increase. Is that true or false? That's true. Yeah, if we compress this into a smaller container, all four gases, we'll see an increase in pressure. What's the balance is going to stay the same. I don't expect a huge difference here. It'll just be heavier overall.
You said that an increase in pressure favors the reactants, but they all still increase in pressure?
An increase in pressure favors the side of the fuel of the gas over here. An increase in pressure favors this. But what they're saying here is this, and this is, you remember that trick question I said? It depends on what you're comparing it to. And what they're comparing to is the original. So, this is it. When I add SO3 to this equilibrium, the amounts of all three substances increases. Is that true or false? If I add SO3 to this equilibrium, the amounts of all three, there are only three, increases. The amounts of all three increase. That's true, right? But what I didn't say is that there's a shift. If I add SO3, it's going to shift left, right? And that means the amount of reactants increases, the amount of products decreases. But it's a bit of a trick question because they're comparing it to the original. And so if I add SO3, then the original, all three of those original ones increase. But if I add the SO3 and I'm comparing it to 1.68, because I'm adding an additional one, so I get 1.68, then it decreased. We went from 1.68 to 1.46. So you have to read the question carefully because sometimes they'll say from the initial perturbed, sometimes they'll say from the original. In this particular case, there is no initial perturb, it's all from the original. So from the original, they all increase. So temperature changes the K value. And so for endothermic reactions, K increases as temperature increases, so it favors the product. So for endothermic reactions, as we increase the temperature, it favors the product here. This is endothermic. And so like endothermic would be melting ice. And so K increases, favoring the product. For exothermic reactions, as the temperature increases, it favors the reactants. And so K decreases. So if I try to freeze water, it's going to be less favorable at higher temperature. But we don't really have to worry about K because we're going to calculate that later. Okay, this reaction I would have expected to be exothermic. And so in Chem 1B, there are two levels of problems. One level problem is you're given the delta H. So when we're given the delta H, we can see this is exothermic. The other level is you're not given the delta H. But if we're not given the delta H, what does this look like? This looks like combustion. You know, we're combusting SO2 to form SO3, just completing that. Combustion reactions are exothermic or endothermic? Exo. In fact, nearly all unless you're trying to burn gold. If you're trying to combust gold, that's going to be highly endothermic, you know, because gold is so reactive. But something like SO2, SO2 is sulfur plus 4, we can completely oxidize it to sulfur plus 6 here. Complete oxidation of this. So I would have expected this to be exothermic. Now, will the amount of SO3 formed from given amounts of SO2 and O2 be greater at high or low temperatures? So high or low temperature. So the way I think about this is it's exothermic. Exothermic is freezing water. Your freezer removes heat. So exothermic is like freezing water. Freezing water is better at low temperature or high temperature? Low temperature. So this is better at low temperature, because it's like freezing water. It's exothermic, low temperature. And so it's favored at low temperatures. Okay, this is N2O4 going to NO2, so we break the molecule. Whenever you break bonds, it's endothermic. So breaking bonds, endothermic, forming bonds, exothermic. And so this is breaking bonds. We're breaking N2O4 into two pieces. That's going to be endothermic. So high or low temperature. Endothermic is like melting ice. Melting ice is better at high temperature or low temperature? High temperature, so high temperature would be the answer there. The enthalpy of formation of ammonia is minus. So forming ammonia is exothermic. Will the concentration of NH3 in an equilibrium mixture with its elements be greater at 100 or 300? It would be 100, yeah. 100 because exothermic is favored at lower temperature. Freezing ice, lower temperature. Not freezing ice, freezing water, lower temperature. All right, let's take a look at some problems in the back of the book here. What can we do? We did these, right? Or did we? We didn't do these? Okay. All right, let me move to these. So what we're going to do is we're going to write some equilibrium. So why don't you try some of these here? 3, 4, 5. Did I talk about Kp and Kc, the relationship between Kp and Kc? Okay. 3, 4, 5, 6, 7. We'll take a look at some of those and then give those a try. Okay, did you guys get A here? What did you get for A?
I've got Kc equals the concentration of NO2 squared divided by the concentration of NO squared times oxygen.
Okay, good. Here, concentration would be molarity, molar concentration. How about B? Did anybody get B?
Concentration is H2 plus divided by the concentration of silver squared.
Okay, that's correct. And then the solid zinc and the solid silver are omitted.
Yeah.
They're not really omitted. They're given a value of 1. And that's called the activity. They have an activity of 1 because the concentration doesn't change. They're pure. How about C? Did anybody get C yet?
I thought the concentration of OH square over CO3.
Good. And then the magnesium hydroxide and magnesium carbonate again. Those are given the value of 1. Here. That's not the concentration. That's what they call the activity. And so you don't have to put that in there. It's just this. Okay, that's good. Now, did anybody get 4? 4 is going to be Kp. But we can just look at it. And what would you say? Kp is equal to?
The pressure of CH4 times the pressure of H2S squared over the pressure of CS2 times the pressure of H2O4.
Yeah, that's correct. Now, one trick or one complication is we know for concentration we use molarity. For pressure, what should we use? Should we use atmospheres or should we use bar? My preference is to use atmospheres, but and most people in America will use atmospheres, but Petrucci is from Canada, and for Canadians, what do you think they prefer to use? Bar. And so it's going to be bar. Kp will be in pressure and bar. That's important because if we use pressure in atmospheres, we might get a different number. We might get a different number if the moles of reactant gas is not the same as the moles of product gas. If the moles of reactant gas is the same, equal to the moles of product gas, then it doesn't matter because if we did the conversion factor would cancel out. However, this is different. We have 5 moles of reactant gas and we have 3 moles of product gas. And so that means a Kp in bar is going to be different than a Kp in atmospheres because the conversion factor will be different in the numerator and the denominator here. They aren't going to be raised to the same power. And so it's going to be in bar. What about 4b? Take a look at 4b and can you tell? Kp is equal to
Pressure of O2
to the 1/2 power. That's correct. And these are omitted from there. But what if I had reversed this? What if I looked at the oxidation? Is silver easy to oxidize? No, silver is not that easy to oxidize. It would be like gold, And so this is probably the exothermic direction. Silver oxide decomposes. Silver we can find as the element in nature, and we're in an oxidative atmosphere. And so since the silver we find in nature is a metal, this is probably going to be exothermic in this direction. Now, if most of the silver found in nature was the oxide, two silvers plus 1 2 gas yields Ag2O. So, if most of the silver found in nature was silver oxide, not silver metal, then I'd expect this to be exothermic. Right? And so here we're using a little bit of experience, like pennies oxidize pretty quickly. If you have a brand new penny, how long does it stay shiny and retain its luster? Not very long. Whereas quarters or dimes, if you have a brand new dime, it retains its metallic luster for a lot longer, right? It's a lot harder to oxidize. And so I expect this is called a formation reaction here, right? We're forming 1 mole of the product from the elements in their more stable state. And so, this is what I think. We could just take a look at the data and then see, what does the data show us? And so I suspect that is endothermic or exothermic based on what I just said. I'd expect it to be endothermic because silver is mainly found in nature as silver metal. So silver metal must be more stable. The silver oxide must be less stable. This is backwards in most metal oxides. Most metal oxides will be exo because, let's say, in nature, most iron is found as the metal, or most iron is found as the oxide, rust. As the oxide. And so most oxides are exothermic, in terms of formation, because it's like combustion. This would be like combustion of silver, but this combustion I would expect to be endo rather than exo, just based on empirical observations. Well, let's test that and then see it is correct. So we can look at some metal oxides, like, for example, magnesium oxide, highly exothermic. Right? Manganese oxide, exothermic. In fact, most of these oxides are exothermic. Nitrogen oxides weren't so exothermic, right? We had some reasons for that, maybe. Let's go to silver. We look at silver oxide is exothermic. So my arguments failed in that case. But one thing is, when we compare the numbers, the next thing we should do is we'll take a look at the numbers. So silver oxide appears to be more stable, but in nature, we find a lot of silver, and it takes a lot longer for silver to tarnish. And so when we compare it to, let's say, iron, this is uphill by what? 31.05 kilojoules, But if we compare that to iron, let's see here. A, B, C, D, E, F, G, H, I. When we compare that to something like iron, let's say rust, iron 3 oxide, that's downhill by 824 kilojoules per mole. And so there's a significant difference in that. And so we know silver jewelry versus gold jewelry. Which one is more valuable? Silver jewelry or gold jewelry? Gold, because it's a lot less prone to oxidation, tarnishing. And so silver is not as valuable. Silver is going to be more reactive. But anyway, that was my guess. My guess is wrong, but in a way it was close. That is, silver oxide isn't as stable as some of the other oxides are. But we have this then, and what would Kp for this be? Yeah, okay, so 1 over the partial pressure of O2 to the 1/2. And so this screws up some people, what to do with the numerator here, because the numerator would be the products, but the product is silver oxide, so what should I use? Well, we use an activity of 1. And so silver oxide has an activity 1, we put 1 there. And so technically it would be just a 1 to the 1 power.
Would you be wrong if you just pulled up the partial pressure of O2 raised to the 1/2 and just made Kp equal to the partial pressure of O2 raised to the negative 1/2?
No, that's fine. It wouldn't be wrong. It's would be fine. So you could do partial pressure of O2 and negative 1/2. It would be fine. So what we want to do is I'm going to get familiar with some of the with some of the numbers. So let's take a look at. I want to show you one more thing. Actually, I'm going to go here. I'll show you one more thing in a bit. We have time, but we're running out of time. So let me go back and take a look at some of these others. So what we want to do is we want to start trying to place numbers with, with observations. And so we'll take a look at, since we only have a couple of minutes left, we'll take a look at this one here. Let's take a look at 7A. Some of the others are really straightforward, but we'll take a look at 7A, and we're going to do K. We have a Kp value of 2.9 times 10 to the minus 2, and we want the Kc value. And so this Kp is at 303 Kelvin. Let's see this question mark. And Kp, the equation is pressure is equal to nRT over V. N over V is molarity. And molarity, if we did it in terms of molarity, would be Kc, and then we have the RT raised to the delta N gas. And so if we're interested in figuring out what Kc is going to equal Kp divided by RT to the delta N of gas. So the first thing we'll do is we'll figure out what delta N of gas is. What is delta N of gas for this? Delta N of gas is a change in the number of moles of gas. And so when I'm looking at it, if I go from 1 mole of gas to 2 moles of gas, what's the change? The change is +1. I'm gaining an extra mole of gas. If I look at B here, what's delta N of gas? So I'm going from 3 moles of gas to 2 moles of gas. Delta N of gas would be -1. I'm losing 1 mole. For C, I'm going from 4 moles to 5 moles. What would delta N of gas be? +1, except that would be wrong for this. What was the mistake I did? Yeah, I counted the solids. I can't count the solids. So we're going from 3 moles of gas to 3 moles of gas, which means delta N of gas is 0. If delta N of gas is 0, then the calculation is very easy, because if this is 0, then this turns into 1, so Kp is equal to Kc. So no calculation required here. Kp and Kc are the same. Here, what's delta N of gas? +1. We're going from 1 to 2. Here, delta N of gas? +2. Good. This one? +2 again. There, this one. So we can figure out what delta N of gas is. Okay, the next thing we got to figure out is what is R? Is R the gas law constant? 0.082. Do you have it memorized for bar or do you have it memorized for atmosphere? I have it memorized for atmosphere as well. And so I would just plug this in, 2.9 times 10 to the minus 2 divided by R. R is going to be 0.08206 to 46 figs, liters times atmosphere per mole Kelvin. But we know that Kp is in bar or atmosphere. Well, Kp is Canadian, so it's going to be in bars. And so this is in atmospheres, this is in bars. Although there are no units, Kp and Kc have no units because in reality they're based on activities. And so we need to convert. And the conversion factor here is that bar is a little bit smaller. They're 1.01325 bar per atmosphere. And so we convert that. And then times T. T will be 303 Kelvin. We don't care about the units. You know, the units aren't really going to work out here. Except for this, you know. But the units really don't work out. And so we just make sure we're consistent within what we have here. Okay, so we can do the calculation. And so if I do the calculation, it's going to be 0.029 divided by 0.08206 divided by 1.01325 divided by 303. And what that's going to come out to is going to come out to 1.15 times 10 to the minus 3 or 1.2 times 10 to the minus 3. There are no units here. But we know that the units for Kc will be in molarity, at least the concentration will be in molarity. Except there's one thing that I forgot to add in here, and that was the delta N of gas. So I'm going to go back. What was delta N of gas for 7A? Delta N of gas was +1. So delta N of gas is +1. This is raised to the first power, so we're okay. I don't have to redo the calculation. So that works out. All right, and we're out of time, so sorry if we went over. So tomorrow, you don't have to prepare for the lab. Tomorrow I'm going to do a modified lab. I was going to do some chapter 16 stuff, but I'm going to reconfigure that so that chapter 16 reactions are going to look like chapter 15. So we'll do it from a chapter 15 approach. So there's going to be no prep. We're going to do some more experimental and some calculations using K and deriving K.
So when you say to bring that sheet signed?
Yeah.
Okay.
Yeah. Can you bring the yellow sheet? Did everybody get a yellow sheet?